So here's our second velocity time graph example. Let's have a read through. So a man travels in a lift from the top floor of a hotel room to reception on the ground floor. So he's travelling downwards from the top floor to the ground floor. The lift accelerates downwards as a constant acceleration of 1 metre per second squared until it reaches a constant velocity of 4 metres per second. So this constant velocity then means the acceleration is zero. So it's accelerating, reaching 4 metres per second, and then keeping that constant velocity. So our acceleration is zero there in that section. And then for the third section of this, we've seen this three-part motion in example 1. It then travels at this constant velocity for t seconds, decelerates until it reaches the ground floor. Okay? And in total, it's telling us this total time. So that's going to give us some information about the area under the graph when we get going with this. First part of the question then, sketch the velocity time graph and then use it to find t. And then the second bit of this question, separately then, sketch an acceleration time graph of what's happening with this motion. So let's get our velocity time graph drawn. So time on the x-axis, velocity on the y-axis. And it's telling us that it accelerates with constant acceleration 1 metre per second squared until it reaches a constant velocity of 4 metres per second. So let's put our 4 metres per second on there. And if it's accelerating at 1 metre per second squared, so that means the change in velocity is 1 metre per second every second, that's going to take us 4 seconds to do that because we want this gradient to be 1. And we could use Suvat there if we wanted to. So we could use a Suvat equation because we could use v equals u plus at. V is 4, u is 0, and then the acceleration is 1, and that would give us the time is 4. So we could do a little bit of Suvat there. So that would give us, if we wanted to, 4 equals 0 plus 1t, so t is definitely equal to 4. So just to convince ourselves, but we could have drawn this anyway, it's not to scale obviously, but because the gradient has to be 1. So there's the first part of our motion. Then travels at constant velocity, so it keeps this velocity of 4 for t seconds, and we don't know what that t is, so I'm just going to put that there, so there's t seconds there. So this time here would be t plus 4. And then it says it decelerates with a constant deceleration of 2 metres per second squared until it reaches back to the ground floor. And again, a little bit of Suvat here, if we have a look at this, or we can just use our common sense from the gradient, but let's do Suvat for a bit of completeness. Velocity at the end here is going to be 0. Initial velocity for that bit of the motion is 4. Acceleration, we're told, is 2, and time is what we're trying to work out. So looking at this, we would get, what would we get? Time equals 2. I should have put a negative in there for my acceleration because it's deceleration. So there we can see where that sign error's come in. That should have been a negative 2, and then rearranging that, we're going to get t is equal to 2. So this last bit takes 2 seconds. And again, we could have done that thinking about the gradient of this. If the gradient has to be negative 2 because it's decelerating, I know my difference in my y values is 4, so this must be 2. So different ways of getting this graph. Suvat will always work, or you can just have a think about gradient and what the graph looks like. So there's the first part of my graph. I'm just putting those dotted lines on there to show us the 3 parts of the motion. Acceleration is 0, deceleration. Okay. So that's the first bit, sketch the velocity time graph. Use it to find t. So using this graph, well, we're given this information, look, the man has descended, this journey in total is 44 metres. So my total distance here is equal to the area under my graph. So my total distance, I'm told, is 44. Again, this is a trapezium. It won't always be, but this is a trapezium. You could do it in separate sections if you want, you know, triangle, rectangle, triangle, but we might as well just do it as one. So a half, A plus B. This time now, excuse me, my total time here, and again, if you want to do it in 3 separate bits, that's absolutely fine, but I'm going to do it as trapezium. My total time here was here was 4, this bit was t, so this bit must have been t plus 4, so this bit was another 2, so this here must be t plus 6. So let's put that in, a half a, which is t plus 6, plus b, which is t, times perpendicular distance between them, which is 4. So 44, half of 4 is 2, 2t plus 6. Sorting this out, 44 is 4t plus 12, so 4t is 32. T is equal to 8 seconds. And if we'd wanted to do that separately, you know, if we wanted to say area 1, 2, 3, that's absolutely fine as well, but just be careful, you know, remember triangles. So half base times height there, rectangle, so 4t for my area there, and then triangle, half base times height again here. That equals 44, and then sorting this out, 8 plus 4t plus 4 is 44, 4t is 32, t is equal to 8, same answer. Okay, so that's that little bit done. Part B, sketch the acceleration time graph. Okay, now acceleration, don't forget, acceleration is the gradient of my velocity time graph. And it's definitely going to be in 3 sections because the gradient for each of these things is different. Okay, so I'm just going to move that up slightly. So now looking at this, the gradient in this first section, the gradient here was 1. So the acceleration is 1. In the second section, the gradient here is 0. It's constant velocity, so acceleration is 0. And in my third section, and we've got to be careful because it's decelerating now, the gradient here is -2, so the acceleration is -2, and that's really important. So on my acceleration time graph, if I put acceleration on my vertical axis and time here, and I know that time is 8, sorry, t is 8 now, so this would have been 14, so I can put that in as well. So this now is my acceleration. We've got negative acceleration going on here as well, so let's get our negative axis drawn. So for the first part of the motion, the first 4 seconds, I'm not drawing this to scale, the first 4 seconds, the acceleration is 1, and it's constant acceleration. You know, the gradient there is a straight line, constant acceleration there, so that's 1. I'm just going to get a different colour here so we can see this. And then between t is 4 and time is 12, so between 4 and 12 seconds, between 4 and 12 seconds, our acceleration is 0. And I'm going to try and draw that on here so that you can see it, hopefully in red. But that's, you know, that's actually on the axis there. That's a is equal to 0. And then for this last part of the motion, a is equal to -2. So that last little bit of the motion between 12 and 14 seconds, acceleration is -2. So we get this really disjointed acceleration time graph, but that's okay because it is 3 completely separate bits of motion: positive acceleration, 0 acceleration, negative acceleration. And sometimes people draw sort of dotted lines here. What you mustn't do is join these with constant lines because it's just 1, 0, -2. So that's our second example done.